Hello everyone, my name is Flavien Lecuyer and I'll present you the work entitled Unveiling the Implicit Knowledge One Scenario at a Time, a work done at INRIA Lab in France. So, this work focuses on the creation of scenarios for virtual reality applications. There are many domains of use for such scenarios, for instance in virtual reality with learning, entertainment, and storytelling. Those scenarios can be useful for different domains, such as medical applications, cultural heritage, or maintenance learning, for instance. The main problem is that creating a scenario for a virtual reality application is quite a tedious process. Of course, it can be done from scratch with computer code, but this needs both the expertise of the developer for the coding part and the knowledge of the domain expert for the semantic of the scenario. And usually, getting the two of them understand each other is extremely difficult because they do not have the same vocabulary and they expect different things from the application. So this takes time and it's strongly error prone. The creation of scenarios can be helped with visual languages, such as the one on the right of the slide, which represents scenarios through Petri nets. And this is the model we'll use during the rest of the presentation. So the graphic representation is a big plus to read the scenario because it helps in understanding the sequencing of the actions, but it still needs to learn some concepts before being able to really use it. There are also methods to automatize the creation of scenarios. The first one is to record the actions of the user and create a scenario based on that. For instance, the illustration on the top right is a previous work we did to record the actions of the user in the virtual environment and translate those actions automatically into a scenario. The main inconvenience with this method is that only one sequence of actions can be recorded, and the scenario created is a simple one. It's a linear scenario with no branching. To get more complete scenarios, we can also use process mining methods, which generate scenarios using multiple observations. As you can see on the right, a surgical process can be recorded manually, input into a process mining algorithm, thus generating a scenario taking into account the variability of the procedure. While it can take into account the variation of the original scenario, it requires some work to annotate the observations for the process mining algorithm. To improve this, we propose an hybrid and iterative method. The first step of this method is to record the actions of the user in virtual reality, creating the observations, and several instances of the same procedure should be recorded. Then, the recorded sequences are merged and generalized using process mining to give a more complete scenario. And finally, the scenario is automatically integrated in the scenario, giving the user the possibility of either stopping there and to record more variations for the generalization, giving the iterative part of the process. So, throughout this presentation, I will mainly rely on an apparently simple scenario, but in fact, it's not that simple. So, this scenario consists in changing a wheel following a cross pattern. For this scenario, there are 8 possibilities. First, 4 possibilities according to the starting point of the scenario, and also for each one of these possibilities, 2 possibilities according to the direction of the pattern. One of these variations, so top, bottom, left, right, is given on the left of the slide. And you can see the expressed scenario on the right with a Petri net. On this scenario, you can see the 4 possibilities at the start, so at the top of the scenario, and the 2 possibilities for each of them once the 2 actions have been done, so on the middle of the scenario. So, as I said before, the first step is the recording of the actions of the user. In the created scenario, each action is translated into a part of the sequence as shown on the right, a transition corresponding to the recorded action, and a new state at the end of the scenario. To be able to detect the actions, we use an internal interaction model, which divides the interaction between the actions, the objects, and the capacities of the objects. As such, once the interaction is triggered, we are able to know which objects are implied and update the scenario accordingly. For each interaction, the list of objects to take into account can also be customized. For instance, the main interaction for the wheel changing scenario, which is tightening the screws, needs two objects, the screws and a tool to tighten the screw. For this particular interaction, we can decide to record the action with either one of the objects, both, or none. In our case, we want to know which screw has been tightened, but we do not want to know with which tool it has been done, so we record the action with only the tightened screw. Here is a short example of how the recording is seen by the expert. As you can see on this video, each time the expert tightens one of the nuts on the wheel, a new part of the sequence is added. This is updated in real time in the virtual environment to show that the action has been taken into account. As you may have seen during the last video, the scenario is also displayed directly inside the virtual environment to help the expert see its evolution. So you have a little example of that on the left figure. The integrated visualization is also complemented with metrics to indicate how the scenario changes between each iteration. On the right figure, you can see that the number of branches, corresponding to the number of possible variations, is displayed. It's the top number on the matrix. And the number of branches that are generated by the process mining algorithm, so the new variations that are not observed, are also indicated both with the number, the second number on the matrix, and also with the blue color on the graph. And those numbers are also complemented with the number between parentheses, which indicates the evolution of those metrics between the current iteration and the last one. As I mentioned earlier, the scenario is also integrated in the virtual environment at each step. Thanks to this, it is possible to see the effect of the scenario directly in the virtual environment. On this short extract, you can see that the screws on the wheel are already highlighted with a white contouring to show that the scenario considers them as a possible starting point. This highlighting can be used by the expert to see if, for instance, one of the starting points is missing in the final scenario. So now let us see how does the generalization work. There are three main steps for the generalization. First, all the recorded sequences are merged into a single scenario by merging the starting and ending states of the scenarios. This global scenario is then converted into a test and flip net, which is a particular class of Petri nets, such as the one you can see on the bottom left of the figure. The main advantage of those test and flip nets is that the format is strongly adapted to the computations done for the generalization process. In itself, the generalization is achieved thanks to a pre-existing test and flip net synthesis algorithm implemented in the Demodocus procedure mining tool. The principle of the algorithm is to compute the test and flip net one place at a time. Each synthesized place forbids at least one action in some context of the scenario. In essence, each place of the network expresses some constraint on the behavior allowed by the scenario. And test and flip networks have been selected among other classes of Petri networks because they are not only well suited to express technical procedures, but also because their synthesis reduces to the resolution of systems of linear equations in the Booleans that can be done in polynomial time. Finally, the generalized test and flip network is converted back into a Petri network to be used as a scenario. The process mining algorithm, and for the cross pattern, we have the following results. With only one sequence, nothing can be done. We only have one observation. With two sequences, the starting and ending states are merged, as you can see on the right. And with a third sequence, some generalization can be done on the scenario, and we have already the 8 possibilities of the scenario. We also tried the method with another scenario, which you can see here, consisting in the assembly of a set of scalpels. This is quite a larger scenario with 92 variations, out of which 12 are redundant, so we only have 80 variations. And it is to note that this is only a part of a bigger scenarios consisting in the preparation of an operation table before a surgical intervention. This scenario is extremely difficult to express by hand. According to my own experience, it takes a lot of time to write, approximately 4 hours with a graphic editor, and it is quite easy to make mistakes during the creation of this scenario because there are a lot of branches that are similar but not exactly the same, so it's really easy to make twice the same branch and miss one. In the other end, with the generalization, 8 sequences, so 8 observations, are enough to get the complete scenario. So, if we consider that we take approximately 1 minute for each sequence, it can be done in only 10 minutes to get the complete scenario. So, this takes significantly less time with the generalization than by hand. Just so you can see it, here is the complete scenario for this problem. As you can see on this graph, there are some transitions in yellow and some in blue, and the yellow ones are the ones that were really observed, and the blue ones are the ones that are generated. So you can see that a lot of them are generated by the process mining, and also you can't really see it on the graph, but some of the arrows between places and transitions are also generated by the process mining, but we did not color encode them here. Finally, we also evaluated our method with some participants. We recruited in total 30 participants, divided in 3 levels of coding expertise. Some of the participants had no coding knowledge, which is expected from a domain expert. Some had some expertise in Unity development. Those are the ones we call the developers. And the rest of them already knew how to use the scenario model, but not the tool we propose here. During the experiment, the domain experts were asked to model a scenario in any way they wanted, while the 2 other groups were only asked how they would do it. We assumed in this case that they already had some experience in creating a scenario before for their own needs. Then the participants tried the tool with first a simple example based on the simplified version of the scalpel scenario, and finally they were asked to create the cross-pattern scenario without any help. They were not guided at all during this last part. At the end of the experiment, we asked the participant to fill out different questionnaires, out of which we mainly processed the U2 questionnaire, but we also asked some questionnaires about the cyber sickness, the presence, and the immersion. We noted great results for the domain experts in the U2 questionnaire, which were confirmed in the post-experiment discussions by the satisfaction those participants had in being able to create by themselves something for a VR application. And you can see on the right two groups of questions for the U2 questionnaire. So the first one is the usefulness, the perceived usefulness for the tool. And the bottom one, you can see that the participants were also ready to reuse the scenario for their work. But you can also see on those two graphs that we are more mitigated and more diverse results for the developers. In fact, this can be, for a part, explained by the fact that the developers are each one their own methods for the representation and the implementations of the scenario. Because of this diversity and this difference between their method and the one we propose, the developers were not as eager as the other ones to change their methods and adapt to the one we propose. In conclusion, now, we proposed a method to simplify the creation of scenarios for virtual reality applications through first the recording of the user actions directly in the virtual environment, and secondly, the generalization of the observations with process mining. This method makes for a faster and easier method to create the scenarios, especially for big scenarios for complex applications. On top of that, the scenario is integrated in the environment as a feedback to help the expert create the more complete scenario possible. Since the scenario is integrated in the environment, this also means that the scenario is reusable directly without any intervention needed from a developer. Another advantage of this method is that it helps in defining implicit constraints for different procedures, since those constraints are expressed through the actions of the user for the first part, and also through the patterns that can be observed and detected during the generalization part. Of course, this work can still be improved. For instance, future works can include taking into account counter examples for the scenarios to explain constraints that should not be possible in the scenario. And it could also be improved by taking into account actions that include multiple users. Thank you for your attention, and here is now the time for the questions, and you also have here on the bottom of the slide the contact information in case you want more information from us.